Geography 607, Week 1. How do you know when you're doing geography? So this week, I want you to watch a video called The Geospatial Revolution. This is all on the readings link in the web page. You're going to read about GIS and spatial thinking, about map scale, and about map types. And then you're going to submit a reflection using the guided questions. And you're going to create a thematic and reference map and discussion, or create a discussion illustrating thematic and reference maps. And then you're also going to turn in a mini map scale lesson. So one of the things that's kind of occurred to me in the past several years is that when I teach math, because I used to teach third grade in alternative high school as well, but there was this set of terms and language that we used when we did math. So if I told students we were going to need to subtract or do a percentage, they knew that we were doing math. In geography, students don't always know that they're doing geography. Often geography is taught within another discipline, and we're doing environmental science, or we're working on a history lesson, and we don't call out those aspects of the work that we're doing that are purely geographic. And so I think students sometimes go through their education not really knowing that they ever took geography or learned any geography. So I propose that we kind of abandon this idea of stealthy geography and not sneak it any longer. You know, we're encouraged to integrate math and let students know that we're doing math and environmental science, and we're encouraged to integrate reading, and we talk about the concepts of both these disciplines, but we don't do that in geography. And so I think one way that we can help address this is to have a very structured set of geographic terms and teach students those geographic perspectives as another set of tools. So there's a work by Gershmill and Bednarz that we're going to be using in this course, and it's a very simple list of terms that kind of set up or identify some constraints for geospatial or spatial concepts. And you're going to there's a reading called Spatial Thinking. It's the summary, and it's a list of terms. It's a list of what those terms might look like. And my goal then is to use these concepts with you as the foundation of each geospatial activity or lesson. For example, in week 2 we're going to use Google Earth, so I'm going to teach you how to use Google Earth in a specific way, but the focus will be learning how to talk about geographic location. So location is a foundational concept. It's the base of most geography. And at the end of the video, there's just this beautiful statement that says the location of anything is becoming everything. And I think this is so exciting and so true today because of globalization, because of geospatial technology and the connections that it makes. So you're going to work with several concepts this term, and here's a list of the concepts: location, condition. I won't read them to you, but we're going to try to work these into the work or to the lessons, have students understand that when they're talking about location, they're doing geography. When they're looking at the connections between places, these are geographic concepts and geographic thoughts. So for next week, you're going to make sure you go through the background reading and videos, complete the 2 labs, the reflection, and submit your work. So just a little bit about map scale. There's a 1.5, 2-page reading that just very briefly talks about maps and scale, and then has you work with math to do some scale conversion. And this is a lesson that I teach in my 151 Digital Earth course, but it's also taken from lessons that I have gotten from a 300 level geospatial course. So just this idea that what is scale, the distance that the map represents is the distance on the Earth of the Earth's surface, and we talk about the different ways to express scale, and I don't know that kids do scale models any longer, but that used to be a nice way to talk about that. So digital representations often have these representative fractions. The graphic scale people are very commonly work with. Word scale, 1 inch equals 500 miles. And then very common is this use of large scale and small scale, but they also get confused a lot, so they're somewhat difficult to use. The representative fraction is the ratio scale, and it means that it's this ratio that has no units. It's the distance on the map as a ratio of the distance on the ground. So for instance, 1 inch on the map, if I were to go out onto the Earth's surface, it would be 100 inches, or 1 foot on the map would be 100 feet, and keeps that unitless. A word statement, 1 inch equals 100 miles, 100 miles to 1 inch, and there's a very close relationship between a word statement and the representative fraction, and one of the math tasks you're going to do is to convert between these two. And it's really important for students to understand scale. Let me go back here a minute. Because when we're looking at spatial patterns and we're looking at connection, the scale has a lot to do with the connections that you see and you want to talk about. So, when you're so digitally zoomed in or zoomed out, it's going to have a lot to do with the patterns and the way those patterns relate to each other. The common scale representation is the graphic scale or the scale bars. And one of the things that students need to know is the scale bar is printed on the map and is kind of hard coded, and so that if you enlarge the map and at the same time enlarge the scale bar or reduce it, they stay in relationship. And they're easy to use, and you can also kind of break it down into increments. Large scale to small scale. I've used this incorrectly more times than I'm even comfortable telling you. I've heard it used incorrectly, and I try not to use it very much anymore because it just sometimes it's just easy to get it a little bit backwards. But so if you need a small scale map of the US, there's a lot of reduction. 1 inch to 2,000 inches is a larger scale than 1 inch to 4,000 inches. And so but what's confusing is the large scale has a larger number, small scale has a smaller number, but 40,000 seems like a larger number. So students have to remember that we're talking about fractions here. Some just general ideas of scale. If I were going to have a map of the world, I would call that a small scale map, and this would be what the representative fraction might be. If I want a topographic map, that would be more a medium scale, 1 to 100,000. The topographic maps I use in class are 1 to 24,000. And then a large scale map might be very detailed plans of a building, so the representative fraction might be 1 to 1,200. So one of the tasks you're going to do is to convert word scale to representative fraction, and one of the things you have to have is common units. So if I say 1 foot, for instance, here's my 1 inch equals 4 miles. So in order to convert this, I need to put everything in miles or everything in feet. And I typically just put everything in, miles or inches. So I usually put everything in inches. And it was amazing to me how many students did not know, these are freshman college students, how many inches were in a yard, and they were not able to make conversions. They weren't sure how many inches in a foot and how many feet in a yard. So that's something you may need to just make sure kids understand. So here's the conversion. 1 inch is equal to 4 miles, and so I'm going to set up some equalities this way. So 1 foot equals 12 inches. I can cross out the inches. 1 mile equals 5,280 feet. I can cross out the feet. I can cross out the miles, and I'm left with no units, which is what I want to do with a representative fraction, I multiply across 1, 2, and here's my 4 times 12 times 5,280. So my representative fraction is 1 to 253,440, and you could round that even to 250,000. Converting it backwards from representative fraction to a word statement, 1 mile, or 1 to 24,000, I would put 24,000 inches because I know that I can use these same units, and so I can cross out inches, I can cross out feet, and I multiply across, and then I need to do the division, so 1 inch equals 0.38 miles. Another task you're going to do is to try to determine what would be the best scale to use to create a map. So if I have an 8.5 inch piece of paper and I'm using 1/2 inch margins, then my finished map size is going to be 7.5 by 10. So if I Google Arizona length and width, I get kind of some general numbers. Arizona is 395 miles north-south and 340 miles east-west. So I know that in order to get Arizona to fit best on the page, I'm going to use portrait because Arizona is longer north-south than it is east-west. So I'm going to set up my 10 inches. I have to be able to get this 395 miles somehow on that 10-inch piece of paper, and my 340 miles on my 7.5 inches of paper. So I have to figure out what is the relationship between those, or how much reduction needs to happen to get this on that size piece of paper. So I'll do the north-south scale first. So I have my distance is 395 miles. There's this many miles in an inch, and so it's a total of this many inches, and then I need to fit this many inches on 10 inches of paper. So my ratio is 1 to 2,502,720. East to west, I convert my 340 miles to inches. I figure out how many, what my ratio is between the total inches in real life and the inches available in paper, and this is my ratio here. So now, which number is actually the smaller number? Because I need to use the smallest number on my paper. Right. This is more reduction. So I need to reduce my map as much as possible in order to get both pieces or both map aspects on the paper. So the mini lab will have you go through these three skills: converting, and then figuring out paper size. Plus there's one other extra little example of converting, trying to figure out what the scale is on a topographic map. Then the last thing I want to show you, I have about a minute and a half, is this website for downloading topographic maps, and it is just very sweet. So you can download free topographic maps. I could type in Eugene, Oregon, and this will go to Eugene, Oregon. I can place a pin. So let's see, I'm going to place that pin right there. And if I hover on the pin, it tells me that there are these topographic maps for this place. So I want the Eugene East 7.5 minute topographic map. I can download this as a PDF and print it off, or I can use Jing. It comes in zipped, so you'll have to, later on we'll talk about how to uncompress zipped files. But the nice thing is that you can grab images from topographic maps for students of to use that are of your area.